Now, before we can answer that question, we must draw a free body diagram. Because how do we calculate the reading on the scale if we don't know where it is in the diagram? Okay, so if you look at the forces acting on the scale, so that's the scale, we have the weight of the object, the person, and then because the scale is touching the floor, there's a force going up from the floor onto the scale. And what do we call that force that goes perpendicular to the surface? The normal force. Yes. They haven't said anything. But even if the lift is going up or the lift is going down, those are the only two forces. If the lift is going up, then the cable pulls on the lift that pushes onto the scale, so that's the normal force. No, because is the rope touching the scale? No.
But it's influencing.
It's influencing the box that will influence the readings. Yes. And we'll get to that just now. All right. Now, did you know? Okay, so let me just ask this. Who has a scale at home? Only the two of you. No one else.
In the past tense.
You had a scale. All right, so the two of you, you have homework and you must come tell the rest of the class. Your homework is to stand on the scale on the floor. Normal floor, stand on the scale. Look at the reading. And then you take the scale and you go put it on the mattress. Okay, or take a very thick, like a blanket, a pillow or whatever. Put the scale on there and then go stand on it again. Right. When you do that, you'll see you get different readings. So when you want to weigh a bit less, then do not stand on the scale on a hard surface, go stand on the scale on a soft surface. Okay? Why? Because the scale doesn't actually measure the force that goes down. A scale actually measures with how much it pushes back onto you. So when they say a reading on a scale, it's actually the normal force reading. So reading on the scale is not Fg. Reading on the scale is with how much it pushes back onto you to keep you where you are. Because when you are on a carpet and you stand on the scale, or when you stand, not on a carpet, on a mattress, the mattress goes in like this, right? So the surface is not hard, so it doesn't push back onto you so much. So when you're on the scale there, the scale or the carpet doesn't push back on the scale that much. It allows it to go in a bit. Right, so it doesn't push back with the same amount. So that is why you will weigh less. Okay, now we're not going to do all of them. I want to do one of A. I want to quickly look at B. Then I want to look at C and D. Okay, says what is the reading on the scale? So calculate the normal force. When the lift is stationary, simple. When something is stationary, which force are we looking at? No, sorry, which force? Sorry, which law? Say again? Which one? Third. No. You know what's going to happen when you say it? Okay, say it. Go for it. Well done. Right, unless a non-zero net force acts on it, but I'll give it to you. No, there's a net force and a non-zero net force. Huh? Say it. Now say net force or result. Alright. So that tells you F net is equal to m times a, but we know there's no acceleration, so it's when the acceleration is 0. Okay? Then, yes? Because you actually get a mark for writing down that, and then you get a second mark for writing down 0. So your choice. Do you want 100% or 50%? There we go. What's the next thing that you must do? Choose a positive direction. So let's say we choose up to be positive. Right? Then we have Fn minus Fg is equal to 0. So Fn is equal to Fg. How do we calculate Fg again? M times G, and G is on Earth? 9.8. So the mass is what? The mass is 50 kilograms times 9.8. And that gives you 490 newtons. Okay. If we did it moving at a constant velocity, which law? Constant velocity? Constant velocity? First law. It would give you exactly the same answer. Okay? Now we're going to look at if it accelerates upwards at 3 meters per second squared. Okay, so it accelerates upwards at 3 meters per second. So that is Newton's Tsebo. When it accelerates upwards. Go for it. When a net force the object will accelerate of the object. Okay. Why did I choose up to be positive? Because it's accelerating upwards. Okay, we want Fn, Fg. We just proved that Fn here is equal to Fg and Fg is equal to 490. Okay, so instead of writing all of that out, I'm just going to write 490. The mass is still 50, and they say he's accelerating upwards at 3 meters per second. So that is times 3. So Zara, what is Fn equal to? And you are grade 11, Zara. You should know how to change it. (640 newtons). Okay, now my question is, when it was stationary, when the lift was stationary, the reading on the scale was 490. Now it is accelerating upwards. Now the reading is 640. Why? Why? Yes, audience? Anyone? Wow? No. Flonnie?
Learn the tension of the cable that holds in the lift. It's taking the thing up, which accelerates upwards.
Okay, so when it accelerates upwards, it must be bigger than the gravitational force. Okay, because it's working against gravity. So not only must you work against gravity, you must make it accelerate faster than what is going down. Okay? Right? So imagine not you in a scale. Imagine you have like a big well, right? And you must pull up water. Okay? Now if you slowly pull up the water, you flip, but let's say you must quickly accelerate it. Will it be heavier or lighter? Heavier. Right? If you just hold the bucket there. Okay, you'll feel something. And now you must quickly pull it up. It will feel heavier because you're working against gravitational acceleration. Okay? And now you must drop the bucket. How will it feel? Lighter. Okay, why? Because you're working with gravity. So you don't have to pull so hard. Yes?
Yes.
Alright, so that is the next question. Then question D is they say it's accelerating downwards. Okay, again, Newton's second law. Now we choose down to be positive. So now we have Fg minus Fn is equal to m times A. Fg is 490. Fn we want to calculate. The mass is 50. And I think they say the acceleration is 5. Okay, so times 5. And what do you get for Fn, Orna? Yes. Because this is a different situation. I want to know what is the reading on the scale when it accelerates upwards, when it accelerates downwards. So it will be different readings. So each time we want to calculate Fn. Here's Orna. Shouldn't get negative. So Fn you take to the other side. And then you have 490 minus 5 times 50. And that gives you 240. So not negative 240, but 240 newtons. So now, like we predicted, if it's going down, it will feel lighter. Okay, so this type of question is a multiple choice type of question. Okay, where I'll say, right, this is the scenario, man in a lift. Okay, the man weighs 400 Newton. The scale's reading is 600 Newton. What is happening with the lift? Right, so you must think, okay, it weighs 400 Newton. The scale's reading is 600 Newton, so it's more than it should be. Okay, so what type of motion will we have? Can it move at a constant velocity then? No, because then it will be the same reading. Is it stationary? No, then it's the same reading. So it's either accelerating upwards or it's accelerating downwards. If the reading is more, then it's working against gravity up. Are you with me? Okay, so the previous page's question with a helicopter and an object there is the same thing. I'm not going to do it now because we are a bit behind. But it's the same concept. About a weight there, how or where is the helicopter moving. Alright, now I want to go to electrostatics. Electrostatics. Alright, now grade 11th. Electrostatics, we started in that extra class on Monday. You write on this whole chapter. So in a lesson and a half, we must complete this chapter and practice it. Okay, so remember we spoke about, is there excess of electrons or a shortage of electrons? Yes, you remember that?
Yes.
Alright, then we spoke about if two charges touch, there's a transfer of electrons until they are equal. And then we spoke about Coulomb's law. Okay, now just a quick recap. When we spoke about Newton's gravitational law, Ntando, you went there at extra classes on Monday. Someone was absent, wasn't there? Oh, yeah. Alright, and Ntando, can you give me Newton's gravitational law in words? I'll start. Any two objects in the universe will attract each other with a force that is. Say again? No, not equal. Ish, anyone helping him out? Proportional to the What of the masses? Product of the masses between their centers squared. Alright, now remember this is if we have big objects. A planet and another planet. The sun and the earth. You're big, and a planet. Okay, so if we have big objects. Now we are busy with charges, electrostatic charges. Charges are smaller things. Alright, now Coulomb's law links. Look at this formula, look at that formula. Looks very similar. Okay, here we are busy with planets and big objects. Here we are busy with charges, charged objects. Okay, so Coulomb's law sounds similar. It says the size of the electrostatic force between 2 point charges. So number one thing that is different is we're not saying force, we're saying electrostatic force. So I'm looking for that word. The size of the electrostatic force between 2 point charges is directly proportional to the product, not of their masses, of their charges. So in metric, if you say directly proportional to the product of their masses here, 0 out of 2 immediately. Even if everything else is perfect. Say masses, it's not masses, it's charges. So the product of their charges and inversely proportional to the square of the distance between the charges. Do you see the distance between their centers? No, because we're not busy now with big things where you have a big radius. You're busy with small things. So we're not going to look at between their centers because the center is like 1 nanometer. Okay, so there's 3 things that change here. In the definition, there's the formula. We spoke about that. We said we only substitute positive values. We looked at how do we calculate the force. Then we looked at if you have 3 charges in a line, how do you calculate the net force. Then we looked at them at an angle. How do you calculate the net force? And now we are busy with the next concept. Okay, electric field. Electric field. So in this chapter, there's 3 definitions that you must know. Coulomb's law, electric field, and then another one that we are going to do. The definition there, electric field is the region. Now, Tatu, what is another word for region? Yeah, just wait a minute. Are there highlighters that are empty? Not. Highlighters that are dry? Not. Okay, sharp. Yes? Call a friend. Who are you calling? Rory? It is a place. It's the area. The Phsc region, the Phsc area. Place. But place is more specific. Region is wide. Okay? So the electric field is a region, an area, in which an electric charge will experience electrostatic force. So it's the area where if you put a charge there, you will experience a force. Okay, so if you look there, okay, there you see we have a negative charge, okay, and just like with electricity, when you have the direction of electricity, it is from conventional current direction, Aurori, with circuits. Is it from positive to negative or negative to positive? Positive to negative. So same thing here. With charged particles, it's away from the positive towards the negative. That is why you see the arrows pointing in towards the negative. Alright? Now, so you have a charged thing here, you have a negative thing here, and there will be almost like having a magnet. There will be electric field around it. In grade 7, you did magnetic fields. Yes? I don't know if you were very naughty or not, but your teacher was supposed to do like a magnetic iron filings where you have 2 magnets with a piece of paper and then there was magnetic things going like that. Were you too naughty? Alright. So, The one class that was well behaved did it. That's my conclusion from this conversation. Anyway, all right. So the same thing here. So you can think of magnets here. All right. So this area where you see these arrows, this is the area where there will be a force. If the arrows are very bright, it means the force is strong. And where the arrows are very light, it means the forces are weak. Now, when we are going to draw it, you look at that page there at the bottom, we are not going to draw a million arrows like this. We draw lines with like one arrow per line. Okay, because we are not going to shade in a test or exam. This is very bright, this is very dark. How do we show it's strong? Is if the lines are close together, it is strong. If the lines are far apart, it is weak. Okay, right, so what is an electric field? It's the region, the area, where a charge will experience a force. Sharp? Okay. Now it says there, they are imaginary field lines, so they are just made up. Okay, you won't actually see there goes a line. We know they are there because of the outcome. The imaginary field lines that indicate the direction of the electric field around a charge. And then few things when you are going to draw them that I look for. Number one is I want to see if you know they extend radially outwards from a point charge, meaning they are more or less like in a circle. Okay? It's not that you have a charge and it goes like this. Okay? They form a circle around it. Then I check to see if you know the direction from positive to negative. So the direction is important. And then they begin and end at right angles. So again, I do not want to see it like this. I actually want to see that you know they go out like this. Okay, so I'm not going to go measure exactly, is this a 90-degree angle, is this a right angle? Just want to see that more or less it's at right angles and that they touch the charge. Then I did tell you that the density is an indication of the strength. So if the lines are close together, then it's a strong field. If they're far apart, it's a weaker field. Okay, those next two bullet points I'm not going to go into right now. So here is an example. You see if it's positive, it goes out from the positive. If it's negative, it goes into the negative. Now you do not have to draw a million lines. 5 lines are sufficient. Okay, here we have how many? We have 8 lines. You don't even have to draw 8. You can draw 5. Okay, when you draw it, you don't have to draw like a million lines like that. A million arrows. 1 arrow per line is fine. If it's at the end or at the beginning, it doesn't matter. Yes. Yes. Right. Then, so normally when you draw it, I'll look for 3 things. So you'll see it counts 3 marks. The next thing is if you have 2 charges that are opposite. Okay, so they're not the same charge. Then I check to see if the shape is correct. Does it go from the positive towards the negative? Okay, and when there are differently charged, same charge, they will repel each other. Okay, now when they repel like this, I do not want to see that the lines cross. If the lines touch or if they cross, you lose their mark. Okay, so if we look here we have a negative charge, here you have a positive charge. You can see that they attract one another. It goes from the positive towards the negative. And if you have the similar charges, you see they repel each other. It becomes dark there in the middle. Yes? Okay. So you must be able to draw this. Then we are going to look at the electric field direction. Electric field direction. Now this is the next big thing that will count 5, 6, 7, 8, 9 marks. The direction of an electric field is the direction in which a small positive charge, that we call a test charge, would move when it is placed in the field. Okay, so when we draw this, okay, then when we draw it like this, you can see I took away the shading now. Okay, because when we draw it, we just see lines. We know it's strong in the middle, weak at the back, weak further away, blah, blah, blah. But we just see lines. So we want to know now, how strong is the electric field here? Okay, are you awake? We want to know how strong is that field. That's the next thing we look at, and which direction is it. Okay, now I just want to do it like it's on your notes, like that. Okay, now if we put, when we want to know that, what we do is we put like a test thing in there to see what would it experience. Almost like when you have a circuit and you want to know what's the volts, you put in a voltmeter. Or if you want to know the current, you put in an ammeter. Okay, to test to see where is this going. Or if you have the river, it has rained a lot, the Fall River, and you want to see how fast is the river actually flowing, right? Then you'll throw in a piece of a stick or whatever, or a leaf, and you'll see how fast does the river go. Yes? Does that stick or that leaf influence the river? No. Not at all. The same thing here. We put in a sensor. We put in something just to test, to see what is there. It's almost like putting in a needle. Okay, now that sensor is called a test charge. Yeah.
It depends how big the stick is.
Okay, you're not putting in a log. Alright, so that sensor we call a test charge. These things are called point charges. This is called a test charge. Okay, now that test charge is a very, 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 very small positive speck. Positive thing, positive point. Okay, that you put in. Now, what do we know about positive and positive? They repel. So if I put that there, you can see that they repel one another. If you bring it closer, they repel a lot. If you take it away, they repel less. Right? What do we know about positive and negative? They attract. So you can see the further away you are, the less the attraction, the closer you come, the bigger the attraction force. Yes? Okay. So now we want to know, if we have a negative thing and if we have a positive thing, what will the electric field strength be between them? Okay? We know it's from positive to negative, but what will it be? Now, if we have this negative thing here, we know that they will repel, positive and positive repel. And if we have this negative thing here, we know negative and positive attract. So we have two forces, two attraction forces. We have a repulsion and an attraction. And if you go back to the first chapter, that is why the first chapter is important and you should know it and have it in your book. Then with the help of the parallelogram method, we can get the resultant field strength. You remember that? Yeah? Okay, so we have this there, and we have the repulsion, and there you have the net force between them. Because if this was gone, it would look different, and if this is gone, it would look different. So the resultant between the two is there. Are you with me? Right, so this is what we have there. We have a positive charge and a negative charge. They are called point charges, and they are capital Q. And when you put that small speck there, it is called a test charge. It is always positive. Always, always, always positive. And that test charge is very small. Okay, it has no influence on the field. And sometimes they don't call it a test charge. Sometimes they just call it a point. Point P or point Q or point Z or point whatever. Okay? So they call it a point. Now, we said positive and positive will repel one another. So it will experience a force in that direction. And positive and negative will attract one another. So what is the resultant between those two with the help of the parallelogram method? It is the resultant there between them. That is why that arrow goes in that direction for that point. Yes? Okay. Now we want to know the strength of that field. Is it very strong there? Is it not that strong? What is it? Okay, so here is the definition for electric field strength at a point. So we had electric field, and then we have electric field strength. So it's two different things here. Strength at a point, and that symbol is E. And it says there, electric field strength at a point is the electrostatic force experienced per unit positive charge. Khali, when you hear the word per, what must you think of? Divide by. Okay, so what must we divide by what? They say there, we must divide force. Hope, what is the symbol for force? F by charge. Oh, yeah. Nyakalo, what is the symbol for charge? Q. So it is force divided by charge gives you the electric field strength. Retabile, what do we measure force in? And relay charge? Coulomb. So that is newtons per coulomb. So electric field strength is newtons per coulomb. Alright, and there you see is the formula that we've just determined. So I've said this before, there is a formula that helps you remember the definition. Because electric field strength is the force per positive charge. Okay, ma'am, here's a lowercase, here's a capital EQ, that you can interchange the two. Okay, lowercase actually just means test charge and big one means point charge, but they won't deduct if you change it for positive, capital or lowercase. Alright, so we have this formula. There's another formula to calculate the electric field strength. It's this one. Where did I get this one? It looks similar to this formula. Okay, what's the difference? Now it's not F is equal to, it is E is equal to K Q 1Q over R squared. Okay, so the 1Q fell away and this became an E for electric field strength there. Okay, now both these formulas are on your data sheet, so you don't have to go memorize them. Right, let's see how we will use them. It says, calculate the size of the force exerted on a charge of 8, weird looking UC, placed in an electric field of strength so much. Okay, let's see, give me anything I can put in my info table. Is 8, now what does that U stand for? Micro, well done. And how do you go from micro to normal? Negative? 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 Nano is 9. Nano 9. It's not 9. And you said you're not done with you yet. What is the symbol for charge? What do I put in front of the equal sign? Q. Right. Cloney, another thing in my info table. Okay, and what is the symbol for that? Electric field strength. E. It's 4 times 10 to the power 4. And they ask what is the force. So we're going to use that first formula. Eh? That first formula. So E is F over Q. Now capital or lowercase, it doesn't matter. And you have 4 times 10 to the power 4. F we want to know, and this is 8 times 10 to the power negative 6. Kutlano, in your head, you can do this calculation. First tell me, what are you going to do? Are you going to multiply or divide? Multiply. Okay, so we're going to say 4 times 10 to the power 4 times 8 times 10 to the power negative 6. What is 4 times 8? What is 10 times 10 to the power 4 times 10 to the power negative 6?
It's 10 to the power negative.
And the unit for force? Newtons. Now, if you checked him on your calculator, you will either get 0.32 or 3.2 times 10 to the power negative 1. Same. Yo, except for those people that are fast asleep. Any questions from the rest?
No, baby.
Khali and Carlo are literally sleeping. And I said this is a grade 12 chapter. That is on you. Okay, last question. It says, calculate the electric field strength at a distance 5 millimeters from a point charge of that. Tsepo, give me something I can put in my info table. 5 millimeters. What do they give us there? There, what's the symbol for distance? That's the unit. What is the symbol? R. Now, Tsepo, do we work in millimeters? How do you go from millimeters to meters? Say again? Wait. Then next thing, wow, in my info table. All right.